M²LINES is a large collaborative effort that includes 9 institutions, including 3 modeling centers. We're focusing on improving 3 climate models: GFDL model, the NCAR model, and the IPSL model. So 2 of those models are developed by a US team, and 1 is a European team.
We need multiple models in order to build trust in the improvements of the representation of these parameterizations we're learning using machine learning for. By improving multiple models at once, we have more confidence that we're actually fixing the physics for the right reasons.
What makes M²LINES so unique is that it's applying machine learning to traditional physics problems. So things that used to be maybe derived in a semi-empirical fashion now can be driven directly from the data. And this is powerful because we're no longer limited by, say, the limits of human imagination or time, but we can really leverage the power of computing to derive a lot of these relationships directly from the data.
The goal of M²LINES is to use machine learning to find missing processes in our climate models, but we need subject experts to link these machine learned structures to the atmospheric, oceanic, and sea ice components in our climate models.
We're explicitly trying to use machine learning as sort of an auxiliary tool in the scientific discovery process in some cases. So using machine learning to discover what information is needed to make predictions, and then also to sometimes discover equations that will generalize better.
Climate models usually are a way to represent the ocean, ice, atmosphere, blend. And what they do is they're numerical simulations. They basically try to solve the appropriate mathematical equations that represent all those components of the climate system.
The first climate models, which got the basic prediction right, which is why he got the Nobel Prize, there is global warming as a result of adding carbon dioxide to the atmosphere. But many details in that model and all of our models since are off, shall we say, and need improvements. For example, that model did not get the extremes right, the weather extremes which we're now experiencing in recent years.
One of the projects in M²LINE will be to represent interaction within the climate system. So we can think, say, about the oceans. We know that the ocean is absorbing a lot of heat and a lot of carbon, and it's happening through mixing and convection. And those processes are much smaller than the grid box size of a climate model. So one of the goals is actually trying to use data and machine learning to represent those mixing processes.
Some of the challenges we struggle with in climate models is that the climate system is so complex and there are so many interconnected processes that when we focus in and study one particular process and try to improve it, we find ourselves affecting the climate system as a whole.
One central goal of M²LINES is to bring deep understanding of the physical processes in the respective domain sciences, atmosphere, ocean, and sea ice modeling. However, these components are not separate, they're interacting with each other. And so we really need to have a broad collaboration between different climate scientists to further improve our climate models.
So ocean turbulence is a complex phenomena, and that is because the flows in the ocean are swirling and evolving at many scales in a nonlinear fashion. And what this results in is that flows that are taking place at very small scales can impact what is happening at the much larger scales or planetary scales. And that is why it is important to understand ocean turbulence, because these small swirls in the ocean impact the circulation over the entire globe.
My subcomponent of M²LINES is dealing with the stable atmospheric boundary layer. So the atmospheric boundary layer is first kilometer or so of the atmosphere. And stable is referring to a situation where you have colder, denser air below warmer, sparser air. Turbulence is a really fundamental force in the atmosphere. So it's going to affect pretty much all the other subcomponents of the climate that all co-evolve together. This is a representation of the smallest scales in the atmosphere. And how they affect the large scales can be extremely important. So because we can't resolve these small scales, we need to derive some way to represent at least their effect in a statistical sense on the larger scale dynamics. What we are doing with machine learning is instead of prescribing these forms ahead of time, we're just giving it the same input that you would give a traditional model, so surrounding values of velocity, temperature information, and from that, letting the machine learning model prescribe turbulent fluxes in the atmosphere.
So when we run climate simulations, both for the oceans and the atmosphere, there is very large amounts of data that is generated. These are on the order of petabytes, and so there is no individual computer that can analyze all of it. It is important to make sure that the data that comes out of M²LINES and the climate simulations is open source, because we would like to get input from a variety of scientists that are part of M²LINES or even part of the larger climate community. One of the ways we're trying to make access to data easier is by relying on an open source community that is called Pangeo. Allows for the analysis that we're doing and the science that we're doing to be reproducible. Because what we are doing is not just limited to the climate centers that we work at, but they're on the cloud, and anyone can come in and run the analysis again and check.
So one of the results we have already is that we can, with machine learning, actually do a better job of representing the vertical structure within the ocean mix layer of the diffusivity profile, which is how heat gets moved around in the vertical. And the result we already have is that it dramatically affects the heat uptake by the ocean.
It's important that we have the best possible climate models, those that have the best representation of the ocean component, the atmospheric component, the sea ice component, and especially the interactions between those components, so that we can adapt and mitigate the effects of climate change in the future.